This video was made in February 2025 for the PRODIGE project by Olga Santos, who is a professor at UNED, president of the International Society on AI and Education, and director of the Physical User Modeling UNED's Research Center, and Miguel Portaz, who is a lecturer and research staff at UNED, Chief of Staff of the Physical User Modeling UNED's Research Center, and Science and Communication Officer at the International Society on AI and Education. When we were asked to synthesize in 20 minutes the research on personalized learning, we assumed the challenge, provided that we could use some little help: generative AI tools. Thus, since the core of the talk is about the usage of AI for personalized learning, we have explored and put into practice some of the possibilities of Gene AI for developing educational material. Thus, the contents of the slides and the video itself have been produced using diverse generative AI tools, but with our expert human guidance and supervision, both to guide the input to the prompts and to make changes to the generated output so that it provides bites of meaningful contents. We will provide some details about the process at the end. Personalizing learning experiences with artificial intelligence technology is not new. At UNED, we have been researching on extending learning management systems with intelligent support for more than 20 years. However, new advances in generative AI are disrupting the educational landscape. In this video, we present some insights of our research covering the three learning domains defined by Bloom: cognitive, affective, and psychomotor, showing how the user model is the key component to integrate personalized features in learning scenarios. Then we outline the main outcomes regarding personalization based on AI that have been addressed by the research community by compiling recent outcomes from the most relevant conferences in the field. After that, the opportunities for personalized learning brought by the large language models are presented, as well as the associated risks and how regulations are being developed to mitigate them. First, some insights based on our background. Let's start with the cognitive dimension. In 2005, we presented the outcomes of the AlphaNet EU-funded project, consisting in an adaptive learning management system designed to personalize the learning experience by integrating educational standards and machine learning techniques. AlphaNet approach foster authors to design learning scenarios based on the IMS Learning Design Standard, adapting to individual learners' needs. It focuses on the different activities performed by different types of users in the adaptation process throughout the entire e-learning lifecycle, which includes design by educational specialists of adaptive standard-based courses, so they can be published in the learning management system. Delivery of adapted learning routes that reference the learning services, such as the forms, where the learning activities have to be performed, and the learning objects that have to be worked by learners with the teacher guidance. Dynamic contextual recommendations during course execution to guide learners and teachers' actions in the course space. On-the-fly building of questionnaires based on the learner's knowledge and experience in the course, as well as metadata defined by the educational specialist. Adapted presentation of the information in the interface of the course, both for learners and teachers. Meaningful reports of the course execution to all the actors involved in the course. Machine learning techniques are to be used to build the user model that can feed the adaptation processes in different ways. Mapping of the course design during the interaction in the learning platform, delivery of recommendations that suggest learning actions to carry out in the course space, modifications of the user interface to highlight relevant information, or creating dynamic questionnaires adapted to the progress of the learner in the course. However, this approach requires a strong effort to conceptualize the design of the course as well as to label the interactions within the course space to train the machine learning models. 5 years later, in the EU for All project, we extended the AlphaNet approach to consider accessibility needs and support the different actors involved to provide educational services in higher education institutions. Again, it can be seen that the user model is key to deliver personalized educational services as it feeds both the recommender system and the content personalization components. This serves not only to recommend learning objects and learning paths to students during their interaction with the course and adapt the user interface accordingly, but also to involve other stakeholders in the delivery of accessible and personalized educational services, such as lecturers, disability officers, transformation officers, and librarians. Labeling of interactions with metadata from educational standards is still needed to train the machine learning models that feed the different adaptation components. In the past decade, we have explored the affective dimension in the MAMAPEC and Big AFF projects funded by the Spanish government. A proper management of the affective state of the learner is crucial to creating a motivating and personalized learning environment. Adaptive systems can detect emotions through facial expressions, body movements, as well as physiological signals. In this case, the user model needs to be extended with information about the changes in learners' affective states while performing cognitive tasks by collecting data from the learner's overall interaction, including their performance on the task and self reported emotional feedback. The goal is to train data mining algorithms that can automatically identify changes in the user's affective state and, based on them, trigger real time interventions elicited from educational experts following user centered design methodologies such as TORMES. In this context, the challenge of labeling interaction data increases as emotions are subjective by nature. Finally, for the last 10 years at the Physical User Modeling Research Center, we have been exploring the psychomotor dimension, which focuses on physical skills and hands on learning. In this case, personalized interventions depend on the physical actions of the learners and can focus not only on guiding the training of motor skills through sensing the performance for the movements, for instance, with inertial sensors, but also to support the embodied learning of cognitive knowledge, such as physics concepts. Recently, deep learning algorithms are being developed to easily obtain the movements of the human joints and guide motor skills, learning based on computer vision. The user model also appears as the key component to guide the personalization, combining information about the movement and the context. Currently, we are also exploring how to integrate the psychomotor dimension within e-learning platforms such as Moodle so that the psychomotor activity is integrated with the learning design of the course, opening the possibility to feed the cognitive processes as well as to get feedback from them. Moreover, we are also exploring the possibilities of immersive learning environments with the use of extended reality. To complement our own research background, let's focus now on a quick overview of the research community by compiling key outcomes from relevant conferences in the field. Remarkably, artificial intelligence is revolutionizing education in 2025, offering personalized learning experiences and transforming traditional teaching methods. The current landscape of AI in education is characterized by widespread adoption across K 12 and higher education institutions, with an increasing number of educators using AI tools. The integration of artificial intelligence into education is driven by several cutting edge technologies that are reshaping how students learn and interact with educational content. Machine learning stands out as a transformative force, enabling adaptive learning systems to monitor student performance in real time. By analyzing patterns and behaviors, these systems can customize content delivery to meet the unique needs of each learner, ensuring a more personalized and effective educational experience. Natural language processing is another pivotal technology, powering AI driven chatbots and virtual tutors that provide round the clock support to students. These tools enhance accessibility and engagement by answering questions, offering explanations, and guiding learners through complex topics at any time of day. Additionally, computer vision and speech analysis plays a critical role in maintaining academic integrity, particularly in online learning environments. This technology is used for facial recognition and audio analysis during virtual exams, ensuring that assessments remain secure and credible. Together, these technologies are revolutionizing the educational landscape by making learning more dynamic, inclusive, and tailored to individual needs. Recent educational innovations are being propelled by some groundbreaking AI applications. Generative AI platforms such as ChatGPT and DALL-E 2 are revolutionizing content creation through dynamically produced interactive lessons, adaptive quizzes, and immersive 3D simulations that respond to student inputs in real time. Simultaneously, AI powered teaching assistants are streamlining school operations by autonomously managing administrative duties like class scheduling, attendance monitoring, and assignment grading, freeing educators to focus on instructional design and student mentoring. Complementing these developments, intelligent tutoring systems now employ machine learning algorithms to deliver instant, personalized feedback during learning activities, analyzing response patterns to detect knowledge gaps and adjust explanation methods accordingly. Together, these technologies form an interconnected ecosystem that enhances both teaching efficiency and learning outcomes across physical and digital classrooms. The educational landscape is poised for radical transformation through different revolutionary AI applications. First, multimodal AI systems will redefine instructional design by seamlessly blending text, visual demonstrations, voice interactions, and dynamic video content, enabling multisensory learning journeys that mirror real world knowledge application. Secondly, AI powered virtual reality will dismantle physical and conceptual barriers, letting learners to explore knowledge through accurate simulations or manipulate 3D structures in immersive VR laboratories, with algorithms adjusting scenarios based on individual progress. Most critically, effective computing breakthroughs will introduce emotion aware AI tutors capable of detecting subtle cues like facial microexpressions, vocal tone variations, and physiological responses, allowing real time content adjustments to alleviate frustration or capitalize on moments of peak curiosity. Together, these technologies will create hyper personalized learning ecosystems where cognitive, sensory, and emotional dimensions harmonize, enabling students to grasp complex theories through tailored experiential pathways while maintaining optimal psychological states for retention. This triad of innovations signals a shift from standardized instruction to context aware education that respects neurodiversity and cultivates intrinsic motivation. Artificial intelligence is fundamentally transforming both traditional and distance education models through three key innovations. First, AI enables content adaptation by dynamically adjusting content delivery according to individual student performance metrics and engagement behaviors, creating bespoke educational pathways that optimize comprehension. Second, it elevates engagement through intelligent gamification systems that craft interactive, game inspired challenges with self adjusting difficulty levels, maintaining learner motivation through evolving narratives and reward structures. Finally, AI breaks down accessibility barriers by deploying specialized tools like real time captioning for hearing impaired students, text simplification for neurodiverse learners, and adaptive interfaces for those with physical disabilities, fostering truly inclusive classrooms. Together, these advancements are redefining educational equity, allowing geographically dispersed students and learners with diverse needs to access tailored, high quality instruction while empowering educators to focus on mentorship rather than administrative tasks. This technological synergy positions AI not as a replacement for human teachers, but as a force multiplier in creating adaptable, student centered learning ecosystems. The integration of AI in education delivers transformative advantages across all stakeholder groups. Students gain AI curated learning journeys that adapt to their cognitive patterns and knowledge gaps, paired with instant feedback mechanisms and interactive simulations that boost knowledge retention. Meanwhile, educators transition from administrative tasks to mentorship roles as AI automates grading, attendance tracking, and plagiarism checks while generating actionable analytics to identify at risk learners. At the organizational level, institutions leverage predictive analytics to optimize classroom capacities, staffing, and budget allocations, while AI enhanced recruitment tools attract top talent through personalized outreach campaigns. This added value proposition creates symbiotic efficiencies. Students receive tailored support, educators focus on high impact teaching, and institutions scale quality education sustainably. Collectively, these advancements establish AI not merely as a technological tool, but as a strategic partner in redefining educational excellence and equity. We have seen that the recent advances on AI can reduce the bottleneck in the course design with the automatic generation of any kind of content, as well as real time chat assistance to learners to clarify doubts and get additional contents. However, this solutions still fail and require further research, and also pose several challenges. The integration of AI in education introduces critical ethical challenges requiring vigilant oversight. Since personalization relies on the integrating meaningful user models in the systems, data privacy emerges as a foremost concern, with sensitive student information, including behavioral patterns, biometrics, and academic records, facing risks of breaches and unauthorized exploitation, as evidenced by public incidents affecting students through compromised proctoring systems. Equally pressing is addressing algorithmic bias, where flawed predictive systems disproportionately misclassify some ethnic groups of students as academic risks, perpetuating systemic inequities. Mitigation demands diverse training data sets, fairness aware algorithms, and third party audits to ensure equitable outcomes. Furthermore, over reliance on AI threatens to erode critical thinking, with studies showing excessive dependence reduces problem solving autonomy and homogenizes research outputs. Striking this balance necessitates AI systems that complement, not replace, human mentorship, preserving opportunities for creative analysis and interpersonal skill development. Collectively, these challenges underscore the need for comprehensive ethical frameworks that prioritize student welfare while harnessing AI's transformative potential. While AI's educational integration accelerates, critical research gaps demand urgent attention to ensure responsible implementation. First, context specific ethical frameworks must address algorithmic bias mitigation and equitable access protocols, particularly for neurodiverse learners and under resourced institutions. Second, longitudinal studies are needed to assess how prolonged exposure to hyper personalized AI tutoring affects metacognitive skill development and social emotional growth. Third, synergistic systems combining AI with other systems, such blockchain, could enable tamper proof academic credentialing and decentralized learning records while maintaining GDPR compliant data governance. Finally, comprehensive AI literacy programs require co design with educators to cultivate critical evaluation of generative outputs and ethical application competencies. Addressing these challenges through interdisciplinary collaboration will determine whether AI becomes an equitable educational accelerator or an inadvertent architect of new digital divides. To successfully integrate AI in education, institutions must adopt a multi layered strategy, beginning with sector specific ethical frameworks that govern algorithmic accountability and prevent surveillance overreach. Concurrently, comprehensive upskilling programs should empower educators to critically evaluate AI outputs and troubleshoot system errors. Technical safeguards and mandatory third party audits, similar to EU's AI Act provisions, must protect sensitive learner data while ensuring model interpretability. Combining pedagogical experts, cybersecurity specialists, and child psychologists could co design adaptive implementation roadmaps. Crucially, students and parents require granular control over data sharing preferences through intuitive dashboards coupled with plain language explanations of AI decision logic. By anchoring these measures in ongoing impact assessments and participatory design principles, education systems can leverage AI's analytical power while preserving irreplaceable human mentorship, creating hybrid learning ecosystems where technology amplifies rather than replaces the art of teaching. Finally, we comment on some risks due to the usage of AI and how regulations aim to limit them. Artificial intelligence regulation, as manifested in the European Union AI Act, seeks to balance innovation with the protection of fundamental rights and security. The main objective is to improve the functioning of the internal market, promoting human centered and trustworthy AI. The EU AI Act takes a risk based approach, prohibiting certain unacceptable AI practices and setting requirements for high risk systems. The Act also promotes AI literacy, ensuring that vendors, implementers, and affected individuals have the necessary knowledge to make informed decisions about AI systems. The AI Office plays a crucial role in developing expertise and capabilities in the field of AI, supporting the implementation of the law and promoting AI literacy. A human centered approach implies that AI systems should serve as tools for people, respecting human dignity and personal autonomy, with the ultimate goal of increasing human well being. This approach requires transparency, explainability, and ethical considerations to ensure user autonomy, trust, and satisfaction. Furthermore, it involves collaboration between humans and AI, leveraging human expertise and ethical values. This is the approach we are following in the CORREX framework. Here we present the Gen AI based approach followed to make this presentation, applied to the educational context. This workflow combines human initiative with AI specialization through a structured collaboration process. It begins when a human operator, either from the student or the teacher, defining a goal through a detailed prompt. To guide the generation of content to meaningful contributions, relevant documents can be added in the prompt. Autonomous AI agents may then divide the task. For instance, one LLM agent for scientific concepts, another identifies interactive simulations, and the others may align content with educational standards. In the case of this presentation, we have combined the following LLM's components: DeepSeek R1, ChatGPT 4.0, Notebook LM, and Perplexity. These specialized agents iteratively refine their outputs through cross-verification, flagging inconsistencies. The synthesized proposal undergoes final human review, where educators assess pedagogical soundness and cultural relevance before approving or requesting revisions. In any case, we advise users to always cross-check AI-generated content for accuracy, particularly in educational or professional settings where academic integrity and precision are critical. For the particular case of this presentation, our experience with the process depends on the kind of contents generated. For the contents based on our background research, the outcomes generated were not very much focused, even though we provided as input relevant papers from our research, and we had to refocus and add details, as well as the snapshots to visually illustrate the ideas. For summarizing the research field, the output was more insightful, and we had just to revise. We also used the Gen AI tools to polish the output and voice the video. Thank you for your attention. Unfortunately, in a 20-minute video, it was only possible to briefly highlight some of the key ideas behind personalization in education. We are happy to further discuss about personalized learning and the impact of AI in the PRODIGE workshops. Please check with Prodigy project leaders for their schedule.